Hello everyone, today is June 8th, 2022. The new problem, case largest element in a string. Design a class to find the case largest element in a string. Note that it is case largest element in the sorted order, not case distinct element. Implement case largest class. Case largest function input integer k and integer array and numbers. Real initialized object with the integer case and the stream of the integer numbers. Return another add function, return the integers and with input integer value. Appends the integer value to the stream and returns a elements representing the case largest element in the stream. Example, so input that's 3 as a k and an integer array for the case largest as 3 as 5 as 10 as 9 and 4, and every time add that will return case largest element. That's expecting return. Count rate. So first one, the k is from 1 to 10,000 and the numbers length is same 0 to 10,000. Numbers read from minus 10,000 to 2 plus 10,000. The value is the same range. At most, the 10,000 calls will be made to the add. It is guaranteed that there will be at least case elements in the array when you search the case element. So far, I don't get the k. What I use? Initialize object with the integer case and stream integers. Why we need a case? Oh, oh, oh. That's always int. Okay, that's always. That means always return the case. That's the case. Okay. Based on the functions, I'm thinking to using the BST binary search tree to store the array. And we also for the new class, the structure case largest, we need absolutely store k. Okay, we need also store BST root tree, and that's number size for the search. So far, we don't need that one. We don't need that one to store in the tree. That's the one. And for the add, add a new insert a new one to the binary search. We need a insert binary search function to do the create a new tree and to return. There's no return for that one. For the search, we do insert that one and we need search case. Yes, we need search case. And for the root tree, I mean, as the previous introduction of the binary search trees, we might be need the count for the tree count for the search later on. So okay, yeah, same things. I'm going to do the implementation back to the Vim. Okay. Case largest element in a stream. Let's see. Okay, that's the one. First one, we need the tree nodes. We need int value, we need int count, we need a structure tree left, we need a structure tree right. Okay, for the insert, we need a function to return the tree node plus new node. New node as the init value for that. I'm thinking the way to get the count update, how we get the count update. But anyway, for the new one, so just such a tree node return then return value equals value, return count equals 0, and return left equals return pointer right equals the none. Return. Okay, that's the one. We do the new node. And similar for the structure keylets. Keys last, we need a structure tree node root. We also need int for keys. Yeah, that's it. We also need add. Okay, so for the insert one, so in this case, define the root node is never be none. Okay, so I'm thinking if I need to return that one. Okay. So, okay, the tree root could be none. Okay, and I'm going to return structure tree nodes as the function return. Okay, if I'm thinking how we could update count. Let me temp if that means if that's root, we just need new node value and the temp count equals 0, return temp. Else means we try to revert. If root value greater than val, the root val, okay, then if root value greater than the val, that means we need search left side, root left equals insert okay, and the root count plus 1. Yes, that's the one. Else right equals insert root right value okay, that's the one, and return root. Yeah, that's good one. So that's good one for the insert the in BST, and after that we're going to try to implement this script. We create that one, and how we could search. Okay, so let me implement the next function, the case largest create. So that's the function we try to get. That's input numbers and the number array numbers and the array size, number size, and try to searching the case as a provided value. Yeah, in that case, I think that's simple. So just we need a indicator I for the loop, and we also need case largest pointer for the return. Okay. Yes, that's the one. And we set k, the k largest structure k to 1, and we also malloc okay, for the malloc we just need for I equals 0, I minus less than numbers the array size, and I plus plus we need call the function insert. Okay, read the root equals insert in BST, and first time we call we could get, we need to get this one, the root, since that's the input root. So first time the root will be the none. After first time call that will generate. Okay, generate the whole tree, the insert all the whole array into the BST tree with the count and the node has been counted update. After that, just return for the case largest structure pointer. Okay, search. Search is kind of the tough function we have to implement. So in that case, let me try to write down something to understand what the search procedure. Okay, let me try to get the root. Root will be, the tree will be like this, 2, 6, 1, 4, 3. So the count will be 1. This count will be 2. This count will be 1. And this count will be, include root itself will be 4. Okay, that's the root. Same thing, 1, 2, 2, 6, 3. So plus 5 root is 7. Okay, when we're searching the k equals the 4. Okay, how we calculate that? So we go, first one we will go to the here to check if the count 7 greater than the k. That means we need to go to his right side, right child. Okay, And in that case, the k greater than 2, so we need to check that side. But since that has 2 biggest, so the new k number will be 4 minus 1 and minus root 1, root 1 itself, so we minus 1. That equals 1. Okay, same thing in the root here. For the fourth, we are searching the 1, but it's bigger, so we go this way. And still bigger than that, we go this way. But in the case there's no right child, we will be check this one, since that will be the largest atom in this subtree. Okay, since we searching the, so in this subtree the k will be equals 1. Okay, it seems the recursive method will be much more straightforward to do implementation. Okay, back to my Vim. Okay, back to the Vim. So first one, there's add k. We have the k in the object. We have insert value. So in that one, okay. So first one, object root will equals insert value to object root, and in the value will be the while. Okay, that's the insert, that's no problem. We'll update that one. After we update, we need what does that need? That need to return a number, so we need this one. So the case largest in BST recursive. We don't need recursive, so that will be the structure tree. And INTK, yes. Okay. Okay, that's same thing, so if let me see, if root not is equals none, so we just return. Okay, so let me check the constraints, so to see. So if we have non-tree, so that means something wrong. So do we need to handle that? So it is guaranteed that will be at this case. Okay, so that's no non-tree, so we don't need to check that one. We just check okay. If the root value, no, not root value, root count greater than k, it must be greater than k, I think. Okay, it must, okay, first one is greater than k, we go, so greater than k, that's greater than k, we go search his right field. If his right field is not real, that means that's only return the root count. If the k count greater than k, so we will search his right child. If root right child is true, we will let me see. Let me check. So if the root child is greater than k, we search his right child. If the root child, let me double think. Okay, we need to check this one. We need to check his root child, right child is true. Okay. Greater than k. If that is true, that has right child. Also, and okay, if that has root child, we could do something here. We also need check and root child. Root right child count. Okay, count greater than k. We just do search root right k. Okay, else if root child is true and right child count. Let me think which way I could equals the enter. Okay, if that equals k, we could simply return as well. Else, if root count greater than k, we could do this, and in the subgroup tree we could combine the greater and the equal. So to here, that doesn't matter. If the count less than k, we just return k's largest root. Is left. It must have left, I think. And k minus 1 minus root right count. Okay, that's the one when we got the root child else. What if root count less than k? That's the problem. In that case, that will be what's the constraint? So the numbers values minus 10. Okay, so in that case, that's something wrong here. We can't. Okay, so the y. So the error, the root, the tree doesn't contain more than case nodes. Maybe I could return minus 101. Okay, for the minus code. Okay, so and the tree count. Free. Okay, invert. Shall be return case. Okay, that will be the case logic free. So void free BST, the structure node tree so. If root right, I choose that's free BST root right. Else, if root left, I choose just free is left. Then free root. Okay, so that's free object tree root. Let me see the root and free the object. That's it. Free the object. If object. If root. Okay, that's the one we do the free as well, so that's the one. Let me review all the implementation here. The tree node has the value left child, right child, and count itself. Structure for the k largest structure that has tree node and case largest number case. New node for the tree that will create a new node and initialize the value to the given value. Count will be 0 and initialize right and left child tree to none. And insert BST that will be do something recursively. So if root is none, so they just create a new one and return the tab. And after that, they will do the left child equals left child to the right. Other than that, we'll do the root right equals the bit. I mean, and in that case, we do the count. We do the count plus 1. The case create, that's simply just called insert BST to insert all the atoms from the array with the size, number size, and also create a node for the k-largest structure. The recursive in k-largest in BST just search recursively, and as the logic we did when the root count equals k, that means we just happen to find the k's largest atom at the root node, so that's return is root. After that, we just check if the root count greater than k, we just check if the right child count is greater than k or not. If greater than k, we just searching the right child subtree with the k, same case parameter. Else, if the right child count less than k, we just searching the left child with the new k value. K will be -1 from the root node, also minus right count. That's a typo as well. I'll correct it. Okay, so that's also the exception handling right here. And add, that's simply just add the new value to the tree and search in recursive. Free, the same thing, that's also recursive free. The BST tree also free the family object. Yes, I think that's all for the implementation. I will do the debug tomorrow. Thank you for watching.